In the last lecture, we left off talking about molecular orbital theory. And we're going to begin part 2 of chapter 1's lecture, talking about how we can apply molecular orbital theory to hybrid orbital theory to make and create new molecules using these molecular orbitals. So a little bit of summary from the last lecture. Each of the orbitals, each of the molecular orbitals, is able to hold up to 2 electrons. And in the ground state, these electrons are going to occupy the lowest energy molecular orbital, and the higher energy molecular orbitals remain unoccupied. So this brings up 2 kind of vocabulary terms that we want to familiarize ourselves with. That is the highest occupied molecular orbital, or the HOMO. This is going to be the molecular orbital of the highest energy that currently has electrons in it, and the lowest unoccupied molecular orbital, or the LUMO, which is the lowest energy molecular orbital that has no electrons in it. These 2 molecular orbitals are going to be interacting with each other when we go to make bonds. So let's take a look at hybrid atomic orbitals. The ground state electron configuration has 4 valence electrons in the 2s and 2p orbitals that we'll be using to make bonds. But the electronic configuration of these does not quite explain how we're going to be able to make 4 bonds that are all similar to each other, 4 equivalent bonds. And so for us to make 4 equivalent bonds, we're going to make hybrid atomic orbitals. If we put some energy into the system, we can excite one of the s electrons up into the p orbital. And then we'll have 4 unpaired electrons that we'll be using to make 4 bonds. Now, we have 3 p electrons and 1 s electron, and these are not equivalent to each other, but we need to make 4 equivalent bonds. So the way that we're going to be able to do this is by making hybrid orbitals. And so if we take our 4 orbitals, our 2s orbital and our 3 2p orbitals, and we average them all out, we can get 4 degenerate or equal in energy sp3 orbitals. In order to form carbon-hydrogen bonds in methane, which is what we're looking at here, we're going to need to have 4 orbitals that are all equal in energy to each other. This will give all of our orbitals the same geometry and allow us to have the overlap necessary to create these new bonds. Now, the shape of these new hybrid orbitals is going to be a little bit different than just the s orbital or the p orbital that we saw before. It's going to have, for an sp3 orbital, or what we've seen here with methane, 1s and 3p orbitals hybridized together. The sp3 orbital is going to have 25% s characteristic and 75% p characteristic. And the shape will therefore be a hybrid of a p orbital that is more similar to an s orbital than just a normal p orbital. So you can see the shape of the lobes is a little bit different. And we can see here in methane, or CH4, our carbon atom is in the center. We have our 4 sp3 orbitals, and in order to make the bonds with hydrogen, they're going to overlap with the s orbital of hydrogen. So we have a bond that's being formed between an sp3 carbon orbital and an s hydrogen orbital. The bond angle for all of these bonds is going to be 109.5 degrees, and this is our standard tetrahedral bond angle. Let's look at ethylene. Ethylene, or ethene, is a carbon-carbon double bond, so we're going to have a little bit different characteristic of our orbitals here. A carbon-carbon double bond consists of one sigma bond the carbon-hydrogen bonds in methane were sigma bonds. The carbon-carbon double bond is going to consist of one sigma bond and one pi bond. The orbitals needed for a pi bond are p orbitals. So when we're looking at the orbitals that we start out with here, we're going to have one p orbital that we set aside for the pi bond. Let's take a look at this carbon on the left here. This carbon is making 4 total bonds. Remember, carbon always makes 4 bonds. 3 of the bonds from this carbon are sigma bonds. It's making a sigma bond to each hydrogen, and it's making a sigma bond to this carbon. So we're going to make 3 sigma bonds and 1 pi bond. The pi bond is going to use a 2p orbital. So we can set this orbital to the side and then use the other 3 electrons to make 3 hybridized degenerate sp2 orbitals. All 3 of these orbitals will be equal in energy, and it's here we have a 3-dimensional figure that displays what these orbitals will look like. In the center we have a carbon atom, and in gray we have all 3 of our sp2 orbitals. In red and blue here, we have the 2 lobes of the p orbital. So you can see the shape of these sp2 orbitals is a little bit different than the sp3 orbitals. The sp2 orbitals shape results from having 33% s character to 67% p character, having a 1 to 2 relationship between the number of s orbitals and the number of p orbitals. And when we're looking at ethylene, so here is a diagram of the entire molecule. We have our carbon. This carbon is sigma bonded to the other carbon with an sp2 orbital. This sigma bond overlap is shown here. We have, so this would be a sp2, sp2 carbon bond. We have the carbon bonded to a hydrogen, so this would be an sp2 orbital overlapped with one of the hydrogen's 1s orbitals. And then finally, we have the p orbital, the 2 p orbitals, one from each carbon, that are overlapping to form the pi bond. The pi bond is formed by the side-by-side overlap of these p orbitals. So the electron density is found both above and below the plane of the molecule. The sigma bonds all form 120-degree angles, and so all 6 atoms here are in the same plane. You can see that's kind of drawn out with this mirror. So they're all in the same plane, and then the electrons that are part of the pi bonds reside above the plane and below the plane. If we want to draw out the molecular orbital diagram of the pi bond, that would look fairly similar to the molecular orbital theory. And we'll have, in the bonding molecular orbital of the pi bond, we'll have the 2 electrons, one coming from each p orbital. And then in the anti-bonding, we'll have a node, and that will be unoccupied. No electrons in that high energy orbital. All right, let's look at another molecule. Here we have acetylene. So now we're looking at a carbon-carbon triple bond. This carbon on the left is going to be making 2 sigma bonds, 1 sigma bond with the hydrogen, 1 sigma bond with the other carbon, and it's going to be making 2 pi bonds. So when we look at our orbitals, we're going to set aside 2 p orbitals for our pi bonds, and therefore our hybrid orbitals that we're using for our sigma bonds are going to be formed with a single s orbital and a single p orbital, making them sp hybridized orbitals. When we look at the 3-dimensional geometry of this molecule, we're going to have 180-degree bond angles when we have sp orbitals. We have between the 2 carbons an sp-sp sigma bond. Between 1 carbon and a hydrogen, we have an sp-s sigma bond. And then we have 2 pi bonds, each formed by p orbitals. When we compare the characteristics of sp3, sp2, and sp orbitals, we're going to have a difference in length. sp3 hybridized orbitals are going to be the longest, and sp bonds are going to be lower. So a single bond is going to be much longer than a triple bond, and that's drawn out here. We can see we have for an ethane, this carbon-carbon sigma bond is 1.54 angstroms in length, and as we increase the percent S of the bond, right, we go from sp3, 25%, sp2, 33%, the length is getting shorter, and finally with acetylene, we have 50-50 S and P, and that's only 1.2 angstroms. In general, we can look at the molecular geometry, or we can identify what the molecular geometry of a molecule is going to be by using the steric number. You can calculate the steric number by adding the number of sigma bonds, so not pi bonds, sigma bonds only, to the number of lone pairs. So for methane, we have 4 sigma bonds, 0 lone pairs, steric number 4. If we have NH3, here we still are going to have the same steric number because we have a lone pair instead of a bond, but we still have 4, basically we have 4 things attached to that nitrogen. Sigma bonds or lone pairs are going to count equal towards the steric number, and with water we have the same. If we have a steric number of 4, then it's going to be sp3. If we have a steric number of 3, then it's going to be sp2. And if we have a steric number of 2, then it's going to be sp. When we went back and looked at acetylene, remember there was, on those carbons there was 2 pi bonds, so it only had a steric number of 2. And we can see, comparing methane to ammonia to water, we're going to have very close to that 109.5 tetrahedral geometry. The bond angle does shrink a little bit as we add in lone pairs, but they're going to have relatively similar geometries. If we look at a molecule like BF3, BF3 is making 3 sigma bonds, but it's only going to have a steric number of 3 because it has no lone pairs. It has no non-bonding lone pairs. If we look at a molecule like BH2, it's going to only be making 2 bonds, and it has 0 lone pairs, and that's going to have more of a linear geometry. We can take a look at these molecules. 20-degree bond angles between the boron-fluoride bonds, and we're going to have an empty p orbital that's orthogonal to those sp2 hybridized orbital bonds. Looking at BE2, BEH2, we're going to have a linear geometry. With a steric number of 2, 180-degree bond angles. So in summary, depending on the steric number, the number of sigma bonds plus the number of lone pairs attached to the molecule, we can determine the hybridization of those atoms. And based on the hybridization, we can determine if we're going to have tetrahedral versus trigonoplanar versus linear. When we have 2 atoms that are adjacent to each other containing different electronegativities, we're going to have a dipole moment. This dipole moment is caused by a partial, like comparing this chlorine here to this carbon. This chlorine is more electronegative than the carbon, so it's going to hog some of the electron density that's shared in that carbon-chlorine bond. So the carbon will be slightly partial positive, and the chlorine will be slightly partial negative. This is going to create a molecular dipole moment, or some directionality with the electron flow. Remember, we're going to have electrons flowing from negative to positive, and just inside this small molecule here, we can see some of that already occurring. And the dipole moment is a depiction of what the electron density looks like within that molecule. In order to determine the net dipole moment, you need to understand the molecular geometry, and this is just going to be a summation of all of the vectors of the individual dipole moments within the molecule. We can look at a three-dimensional view of this effect called an electrostatic potential map, and this is similar to a heat map, but instead of looking at hot and cold, we're looking at negative and positive. So we can see in chloromethane, chlorine is more electronegative than carbon. It's hogging that electron density in this bond, so therefore the chlorine gets a partial negative and the carbon gets a partial positive. The heat map shows that electron density differential depicted with red around the chlorine and blue around the carbon. When we're looking at the different solvents that we're going to use in organic chemistry, the different liquids that we're going to use to dissolve organic molecules and salts to react them together, we want to keep some of these dipole moments kind of at the front of our mind. They're going to have different effects on reactivity and different effects on solubility. So this dipole-dipole interaction is just one of the several different types of intermolecular forces that are going to affect the properties of the molecules. Some of these include the solubility, the boiling point, the density, if it's a solid versus a liquid. Molecules that are neutral are going to be attracted to each other through these different interactions, specifically the dipole-dipole interactions. You could think of it as the the negative that's built up in a dipole-dipole interaction on one atom is going to be attracted to the positive that builds up in a dipole-dipole interaction on another atom. And a couple other forces that we want to look at are hydrogen bonding and dispersion forces. So here we have acetone, and acetone has a carbon-oxygen double bond. Oxygen is more electronegative than carbon, so the oxygen is going to have a partial negative charge, the carbon is going to have a partial positive charge, and there's going to be a net dipole moment towards the oxygen and a negative out here. What we're going to have is a stabilizing effect when we have two of these acetone molecules front to back, because this negative charge is stabilized by the positive charge on the carbon of the adjacent atom. This stabilizing interaction is actually going to increase acetone's boiling and melting points. Acetone is a very small molecule, very small molecular weight, and molecules of a similar molecular weight would have a much lower boiling and melting points without this interaction. You could see isobutylene, all carbons and hydrogens, so we have no dipole moments in this molecule. It's going to boil at -7 degrees Celsius, so that's far below room temperature. That's below freezing even. And acetone is going to boil at 56.3 degrees Celsius. The molecular weight difference between these molecules is almost none. Let's take a look at hydrogen bonding next. This is one of the strongest interactions and one of the most common interactions between atoms. Hydrogen bonding is the attraction between the partial positive and negative charges of hydrogen atoms with lone pairs. So here, let's look at water. Oxygen-hydrogen has a pretty large electronegativity difference, so we're going to have a partial positive on the hydrogen atom. This oxygen is going to be hogging most of the electrons in this oxygen-hydrogen bond. On a lone pair on the oxygen is going to be very electron rich, and so we're going to have a stabilizing interaction between this hydrogen and the lone pair attached to the oxygen, and this occurs with both water and ammonia. It's an attractive force between a hydrogen bonded to another electronegative atom. So notice that if this were a carbon, this interaction wouldn't occur. The hydrogen has to be attached to an electronegative atom such as nitrogen, oxygen, or fluorine. Overall, the strength of this interaction comes with the notion that there are many, many hydrogen bonds occurring. For example, in water, all of those different water molecules are hydrogen bonding to each other. So the individual interaction itself is not that strong. Hydrogen bonds are still 20 times weaker than a covalent bond, but the fact that so many of them are occurring is what gives us many of the properties for molecules like water. So let's talk about solvents again. Solvents are going to be a really important factor in a lot of the reactions that we learn, and we're going to have to be able to attenuate the properties of the solvent we want based on the characteristics that we desire. Solvents that have the ability to do hydrogen bonding, meaning they have a hydrogen attached to an electronegative atom, are called protic solvents. So acetic acid is a protic solvent. We have a hydrogen attached to an oxygen. Solvents that do not have the ability to become hydrogen bond donors are aprotic solvents. So for example, dimethyl sulfoxide has hydrogens that are only attached to carbons, as does diethyl ether. Hydrogen bonding also affects the boiling point of a molecule. So in trimethylamine, we have a methyl group attached to each of the sites of the nitrogen. We have no hydrogen bond donors, very low boiling. Ethylmethylamine, we have a nitrogen-hydrogen bond, so we have a hydrogen bond donor, and this is going to be able to donate to another lone pair on a different nitrogen. That's going to increase the boiling point, stabilize the interactions. It's a stabilizing interaction. And propylamine, we now have two nitrogen-hydrogen bonds that can act as hydrogen bond donors. So we're going to have an even larger boiling point due to a larger amount of hydrogen bonding occurring. In biochemistry, you'll spend a lot more time looking at DNA, or in genetics. DNA is a spiral, and the structure of this spiral, this alpha helix, is stabilized and caused by hydrogen bonds between the different strands of the protein. So some molecules might not have a dipole moment, and they also might not have hydrogen bonding, but there's still going to be some attractive forces between them that act as stabilizing forces, and these are called London dispersion forces. So nonpolar molecules will generally have their electrons spread out evenly around the nuclei to balance out the charge, but these electrons are in random motion. So you might see, even though these molecules are all carbon hydrogens, we have no dipole moment, that as the molecules line up head to tail, we see that the balance of charge is not evenly distributed between the nuclei, and this uneven distribution allows for temporary dipoles that will have a stabilizing effect for the molecules. This is going to be the weakest interaction of the three that we've looked at, but the more types of interactions that we have, um, if there are enough of them, they can add up to become a fairly significant interaction. We can see how this interaction of London dispersion forces affects the physical properties of the molecule by looking at the boiling point. So if we start with butane, 4-carbon chain, we're going to have a boiling point of 0 degrees Celsius. As we add extra carbons, so with pentane we've added 1 carbon, that's going to increase the surface area of the molecule and therefore also increases the boiling point. And with hexanes, an extra carbon even further increases the size of the molecule and the amount of surface area, leads to more of the London dispersion forces stacking up with the different molecules. We're going to have more attraction between the molecules and an even larger boiling point. As we branch the carbons of the molecule, we're actually going to weaken the London dispersion forces. All 3 of these molecules have the same number of carbons, same molecular weight. In pentane, we have a linear chain. These molecules are going to be able to stack very nicely on top of each other. The surface area and the surface area where they're able to interact is quite large. As we begin to branch the molecule, it'll be more difficult for these molecules to stack on top of each other. Less surface area will overlap, and we're going to have less interaction between the molecules, which leads to a reduced boiling point for 2-methyl butane and an even more significantly depreciated boiling point for 2,2-dimethyl propane. As you learned in general chemistry, like dissolves like. So when we're thinking about what type of solvents we're going to want to use to dissolve specific molecules, we can generally think about polar compounds mixing well with other polar compounds. If a compound is able to form hydrogen bonds and has dipole-dipole interactions, then a solvent that has dipole-dipole interactions and is able to form hydrogen bonds like a polar solvent will generally work well. If we have a nonpolar compound that only really contains London dispersion forces, then we might want to look towards a nonpolar solvent. At the interface between nonpolar and polar, we have detergents and soaps. So this compound is going to contain a polar head, a polar group that's hydrophilic and loves water, can hydrogen bond quite easily, and it's going to have a nonpolar group or nonpolar part of the molecule. And what this allows us to do is to take nonpolar molecules and dissolve them into water. And the way it does that is through forming a micelle. Each individual circle and string here is one of those soap molecules, and they're all going to orient themselves in such a manner that they form a ball. On the outside of the ball, we'll have all of our water molecules interacting with the polar groups. And on the inside, shielded from all of that polar hydrogen bond and dipole-dipole interactions, we have all of our nonpolar groups that are interacting with the oil molecules. So it's in this way that we're going to have soaps get to carry away oils and dirts and dissolve them into water.